Hello, this is Professor Roman. Let's continue our discussion of linear transformations and isomorphisms. A consequence of what it means to say that isomorphic vector spaces are essentially the same is that for each field F and each cardinal number kappa, whether it be finite, that is a natural number, or infinite, there is essentially only one vector space over the field F with dimension kappa. Here is the formal statement. Let V and W be vector spaces over a field F, then V and W are isomorphic if and only if they have the same dimension. Or in looser terms, V and W are essentially the same vector space if and only if they have the same dimension, which is why there is essentially only one vector space of each dimension. One could also phrase it, and I think you'll hear this more often than not probably, that there is up to isomorphism only one vector space of each dimension over a given field F. So in particular, if the dimension of V is equal to n, and that's a finite cardinal, so it's natural number, then V is isomorphic to Fn. So the up to isomorphism, the unique vector space of dimension n is just Fn. Or put even more loosely, all n-dimensional vector spaces over F are essentially just Fn, ordered n tuples. An isomorphism, as for the proof, an isomorphism, tau, from V to W, will send a basis for V to a basis for W. This we already proved. And since tau is injective, it actually is a bijection between the two bases, and so they have the same size. And therefore, V and W have the same dimension. Conversely, if V and W have the same dimension, and if we take a basis for V and a basis for W, we can define a set function that maps a basis element in B to a basis element in C bijectively. This can be extended by linearity to a linear transformation from V to W that takes a basis to a basis and is therefore an isomorphism. And so V and W are isomorphic. So this theorem implies, again, that at least for natural numbers, all natural numbers n, the n-dimensional vector spaces over F are essentially just Fn. There is an analog for vector spaces of arbitrary dimension kappa. So kappa could be a finite cardinal, in other words, a natural number, or it could be an infinite cardinal. Now one might think at first that it ought to, the analog of Fn ought to be F kappa. But when kappa is infinite, there's a problem. This is actually too big. We know that the dimension of Fn is n, but the dimension of F kappa is not equal to kappa when kappa is infinite. Here's an example. for the base field F, let's just take Z2, which is the set containing 0 and 1. And for kappa, we can take the smallest infinite cardinal, all if not. Then F kappa is the set 0, 1. So this is the set of functions from the natural numbers to 0, 1. But what is such a function? It's just a characteristic function of a subset of the natural numbers. Every one of these functions identifies a subset of the natural numbers, namely the natural numbers that go to 1. And for every subset of the natural numbers, we can define a function, the indicator function from n to 0, 1. So this is in one-to-one correspondence with the subsets of the natural numbers, or in other words, the power set of n. And we have seen in earlier lectures and in the appendix to the book that the power set of n is strictly larger than n. In fact, the power set of n has cardinality equal to the power of the continuum, the same as the real numbers, which is strictly bigger than all if not. And from this fact about cardinality, we can prove that this vector space cannot have a countable basis, because if we have a countable subset that is linearly independent, so each of these b's are actually functions from the natural numbers to the set 0, 1, then the linear span of these functions is the set of all linear combinations of these functions, but a linear combination, because the scalars are either 0 or 1, a linear combination is just a finite sum. And since order doesn't matter, there's a bijection between the vectors in the span of this set and the finite subsets of this set, because linear combinations which reduce to sums are finite sums, so they only use finite number of these at a time. So the span of S is in one-to-one correspondence with the finite subsets of this set, and there is a theorem in the appendix that we also discussed in an earlier lecture, that the cardinality of the set of finite subsets is the same as the cardinality of the set, so all if not. So in short, S spans a countable set of vectors, but the vector space is uncountable, power of the continuum. So S cannot span all of the vector space and therefore cannot be a basis. So this vector space has uncountable dimension. And that's why it is not suitable. It doesn't have dimension n. So in this case, it's not the analog that we want of Fn having dimension n. This vector space does not have dimension kappa. It has larger dimension. Well, that's not a serious problem. We're just looking at the wrong analog of Fn. The right analog for this purpose is F kappa naught, which is the set of all functions from kappa to F that have finite support. In fact, the standard basis for Fn naught, F kappa naught consists of the characteristic functions. And these are maps from kappa to F. Kappa is a cardinal, but don't let that upset you. It's just a set. It's a set of cardinality kappa, but all we care about now is that it's a set of that has size kappa. We don't need to know what a cardinal number actually is. So the chi sub a, chi is, this is the Greek letter chi, chi. Subscript a belongs to the cardinal kappa. Chi sub a of x is 1 when x is a and 0 otherwise. So it picks out the element a from the set kappa. And these functions are the analogs of the functions e1 through en, the standard basis vectors in Fn. The chi sub a, where a ranges over the domain kappa. And I'm going to leave it for you to verify that these do in fact form a basis. You can see immediately that they span F kappa naught. The naught is important because the span only gives you finite linear combinations, so you're only going to get functions with finite support out of these characteristic functions. Okay, I'll let you fill in the details on that. So the dimension of F kappa naught is the size of kappa, or the cardinality of kappa, because there's one of these per element of kappa. And as I said before, kappa, being a cardinal number, is its own cardinality. So this is the vector space that has dimension kappa, and this is the proper analog of Fn when we're dealing with infinite cardinals. So in summary then, if n is a natural number, any n-dimensional vector space over F is isomorphic to Fn. So there's only essentially one vector space of dimension n, namely Fn. More generally, if kappa is any cardinal number, then any kappa dimensional vector space over F is isomorphic to F kappa naught. And so that is, up to isomorphism, the only vector space of dimension kappa. Of course, part 2 covers part 1, because kappa can be a finite cardinal, which means it's a natural number n, and then the subscript naught does nothing, because all functions must have finite support, since the domain is finite. So, for every cardinal number kappa, whether finite or infinite, there is essentially only one vector space of dimension kappa. I guess I better say over the field F. Don't let that distress you too much. It does not render linear algebra trivial by any means. Okay. There are still plenty of essentially different vector spaces. And of course, this is a theoretical result as well. In a given context, a physical environment or computer science or whatever you're working in, the elements of the vector space have meaning, and so just because two vector spaces are isomorphic certainly does not mean they're interchangeable. It only means that they have the same linear structure, but they're still different if the underlying sets are different. There is another viewpoint, another way to think of isomorphisms and linear transformations in general that is quite important because it represents a point of view that does occur frequently in mathematics. It goes by the general name of representation theory. Here's a definition. Let V and W be vector spaces over a field F. Any linear transformation, tau, from V to W is called a representation of V in W. And a vector, little v in V, is said to be represented by the vector tau V in W. This is not new mathematics. This is just another way to look at linear transformations as representations of vectors in the domain using vectors in the codomain. It's a state of mind. It's a point of view. An injective linear transformation is called a faithful representation, and each vector is said to be faithfully represented by its image. Faithful is a reasonably good word because injective linear transformations are reversible. Each vector in V is represented by a different vector in W. So if you know the representation, you know the original vector. A surjective linear transformation is called a full representation, simply because every vector in W represents something from V. And a bijective linear transformation, in other words, an isomorphism from V to W, is called a fully faithful representation of V in W, and its inverse would be a fully faithful representation of W in V. This is a language that I'm going to use as often as I feel appropriate, so you will get used to it. If you study more advanced abstract algebra, you may study, for example, group representations. And there are other forms of representations throughout mathematics. It's just a particular point of view. Of course, faithful representations are nicer than non-faithful ones because of the very fact that every vector in V is uniquely represented. I'm sorry, that's actually not what I wanted to say. Every vector V is uniquely identified by its representative. Okay. But we can't always find useful, faithful representations. Sometimes the best we can do is a non-faithful representation. And I'll give you some examples in a minute. They are still quite useful, even though you can't determine from a representation which vector is being represented. Still, this point of view has value. So some examples. The isomorphism we talked about earlier from the polynomials of degree at most n to the n plus 1 tuples, this is then a fully faithful representation of polynomials as ordered n plus 1 tuples. The other direction also is a fully faithful representation, but I think one would tend to want to represent polynomials as ordered n tuples more often than going the other way. But that I guess I'm not sure really. The map tau that maps an m by n matrix to an m plus n tuple, defined by simply stringing out all the elements of the matrix in one tuple. It would be an n plus m. I'm sorry, it would be, n times m. M times n. Nobody ever said a mathematician can do arithmetic. Whoever said that didn't know any mathematicians. Okay, a matrix of size m by n, of course, has m times n entries. Anyway, this is an isomorphism, and therefore a fully faithful representation of matrices as mn tuples. We will see later on that the map lambda that sends matrices of size m by n to linear maps from Fn to Fm, again note the reversal, defined by lambda of a matrix A is multiplication by A. This is a linear map. This is a fully faithful representation. It's an isomorphism. Therefore, a fully faithful representation of m by n matrices as linear maps. Every matrix is represented by a linear map. Matrix A represented by the map multiplication by A. The inverse map, lambda inverse, represents linear transformations as matrices, and that is the more common direction. And we're going to talk about that representation at some length. Basically what it tells us, because this is fully faithful, is that every linear transformation between Fn and Fm is nothing more than multiplication by some matrix. And we'll go into that in detail. If n is bigger than or equal to 2, and we let sigma map F to Fn, sigma of A simply sticks A in the first component of an n-tuple. This is a faithful representation. If you have an n-tuple, you know precisely which element of F is being represented by it. It's simply the first coordinate, the first component, rather. But this is clearly not full, because there are plenty of n-tuples that don't have all zeros except in the first coordinate. So faithful but not full. The right shift operator on the sequence space is faithful but not full, whereas the left shift operator is full but not faithful. And you should think about that until it seems rather clear. The trace function that sends a matrix to its trace, the sum of a square matrix, sum of the diagonal elements. This is a representation of matrices as scalars. It's much like the representation of a set of test scores by using their average. You represent a data set by a single scalar. Students seem to be very intent on knowing what this representation is after every test, even though it's of much less value than it may seem. in any case, the trace is a full representation. Every scalar in F is the trace of some matrix. You can just stick that scalar in the first entry of the matrix and put zeros everywhere else, and the trace will be that element. But it is very far from being faithful. There are many matrices with the same trace. The determinant also is a full but not faithful representation of matrices. So I guess that tells us that we cannot say that non-faithful representations are not very useful. The determinant and the trace are quite useful. There are two very important vector spaces associated with a given linear transformation, tau from V to W. Vector spaces other than V and W. And here is the definition for tau mapping V to W. The set of all vectors in the domain V that are sent to 0, the 0 vector in W, looks like this. The set of all V in V such that tau V equals 0. This is a subspace of V called the kernel of tau, written K-E-R of tau, also called the null space of tau. The dimension of the kernel is called the nullity of tau, and I'll denote that by NULL of tau. I'm going to leave the proof of this theorem to you. It's not very difficult to show that this set is closed under linear combinations. On the other side, the set of all vectors in W that are images of vectors in V, under the map tau, of course, this is simply the image or range of the function. Doesn't matter whether linear or not, this concept is defined for all functions. So we call that the image or the range of tau. And the dimension of the image of tau is called the rank of tau. And I'll denote that by RK of tau. So we have the kernel and we have the image, also known as the range. These two subspaces, one is a subspace of V, the other is a subspace of W, are strongly related to the surjectivity and injectivity of a linear transformation. And here's the theorem. Tau is a linear map from V to W. Tau will be surjective if and only if the image of tau is W. That's got nothing to do with linearity. That's simply the definition of a surjective function. Its image is equal to its codomain. This is the more interesting part. Tau is injective if and only if the kernel of tau is 0. So as to the proof of part 2, if the kernel of tau is trivial, then to check for injectivity, we set tau u equal to tau v. We have to show u equals v. Well, by linearity, we can write this as tau u minus v is 0, or u minus v is in the kernel of tau, which is trivial, and therefore u equals v. Conversely, if tau is injective and u, is that a u? It's a v. V in the kernel of tau, then tau of v will equal 0, or in other words equal tau of 0. And so the injectivity implies v equals 0, and so the kernel is trivial. This is a very simple proof, especially in this direction, but it works only because tau is linear, and we're dealing with a linear structure. It's definitely the way to show or decide whether a linear map is injective. Check the kernel. Examples: tau maps 2 by 2 matrices to polynomials of degree 1 or less. Tau of the matrix ABCD is A plus D plus quantity B plus C times X. The kernel of tau is the set of all matrices that are sent to 0, which means A plus D has to be 0, B plus C has to be 0, and so the matrices have to look like this: A, B, negative A. This subspace, this is the kernel of tau. It's therefore a subspace of M2 of F. The range is all of F1 square bracket X, because you can get any polynomial you want here from an appropriate matrix. The kernel of the left shift operator, this is all the sequences that get sent to 0 upon a left shift. So it doesn't matter what's in the first coordinate, because it's going to disappear after we shift it, after we shift the sequence. But we got to come up with all zeros after the shift, so the rest of the sequence has to be zeros. So this is in fact isomorphic to the base field itself, the kernel of tau. The image of tau, what sequences can you get after shifting one to the left? Answer: any sequence. Pick the sequence you want, but start that sequence at the second coordinate. Put anything you want in the first coordinate. Left shift will produce that original sequence. Kernel of the right shift operator looks like this. It's trivial. Now you're shifting to the right. You expect all zeros. You had better have started with all zeros. And this is what the image looks like. For a matrix transformation mu sub A, here's an example of this particular matrix. To find the kernel, we perform some reduction, produce a matrix in reduced row echelon form. So it's PA, where P is invertible. And because P is invertible, AX is 0. In other words, X is in the kernel of A if and only if PAX is 0. So these two matrices have the same kernel, or the corresponding transformations, mu A and mu PA, have the same kernel. And it's easy to check the kernel here, which vectors get sent to 0, and it's precisely this vector. Okay. And any scalar multiple of this vector. So the kernel is the subspace spanned by this single vector. It's a one-dimensional kernel. We should also note that the concept of rank and nullity is defined directly for matrices. That's usually done in an elementary course. But it's also defined for linear maps, such as mu sub A, multiplication by a matrix. But because the image of mu sub A is the same as the column space of A, and the kernel of mu sub A is the same as the null space of A, the ranks of the matrix transformation mu sub A and the matrix A are the same. They're not quite defined the same, but they are equal. And the nullity of mu sub A is the same as the nullity of A. It follows then that the matrix transformation mu sub A is surjective if and only if the rank of the matrix is equal to m. That's the number of rows. And mu sub A is injective if and only if the nullity of the matrix is 0, or the nullity of the matrix transformation is 0. And according to the Rank-Nullity Theorem for matrices, which is in Chapter 1, and I don't think I covered it in the lectures, saying that the nullity of a matrix is 0 is the same as saying the rank is equal to the number of columns. So here's the summary. Mu A is surjective if and only if the rank of A is the number of rows. Mu A is injective if and only if the rank of A is the number of columns. So for a square matrix, same number of rows and columns, you can see immediately that mu A is surjective if and only if it's injective. Okay. And we'll come back to that in a minute. Let us now examine the famous Rank-Nullity Theorem for linear transformations. And that would include matrices because it includes matrix transformations. So let's let tau be a linear transformation from V to W. We know that any subspace of V has a complement, so that includes the kernel. So let's call a complement T and fix it. There will be many complements to a subspace in general if it's a non-trivial proper subspace, but we only need one, so we'll fix it at T. Now, if we restrict the map tau to T, it becomes injective, and this is the reason. The kernel of the restricted map consists of the vectors that, first of all, must be in T, because that's the domain of this restricted map, but they also must send the vectors must be sent to 0 by the restricted map, which is the same thing as saying they're sent to 0 by the original map. So the kernel of the restricted map is the intersection of T and the kernel of tau. And since T is a complement of the kernel of tau, this intersection is trivial. So that makes this map injective, the restricted map. As to the image of the restricted map, it is the map tau applied to the full domain, which is T. And we can apply tau to, here is tau applied to T again. This is tau applied to the kernel of tau, which is trivial. So all I've done is place the trivial subspace here, but written it this way, because then tau of this sum, the tau of the kernel plus tau of t is the tau of the sum, which is direct, and that's tau of v, which is the image of the full map tau. So the restriction to t is injective, has trivial kernel, but has the same image as the unrestricted map. And that makes a lot of sense, because in a sense, what we've eliminated, well, specifically what we've eliminated from the domain when we did the restriction is just the kernel, which gets sent to, everything gets sent to 0, so it's not going to affect the image. So, if we also restrict the codomain from W down to the image of tau, we get an isomorphism. The restriction of tau to t is an isomorphism from t to the image of tau. So these are in fact isomorphic. So the dimension of v is the dimension of the kernel of tau plus the dimension of t, because these two are essentially disjoint, and their sum is all of v. And this is just a repeat here, but the dimension of t is the same as the dimension of the image of tau, because t and the image of tau are isomorphic. So that is the Rank-Nullity Theorem. Here is the theorem in some more detail. First of all, V and W are vector spaces, tau's linear map. Every complement of the kernel is isomorphic to the image of tau. T is isomorphic to the image of tau. Be careful here not to misinterpret. A complement of the kernel of tau is not equal to the image of tau. It's not even in the right vector space. It's not in the codomain, it's in the domain. But it is isomorphic to the image of tau. The Rank-Nullity Theorem now says that the dimension of v is the dimension of the image plus the dimension of the kernel of tau. Or in other notation, dimension of v is the rank of tau plus the nullity of tau, hence the term Rank-Nullity Theorem. It follows from this that tau is injective if and only if the nullity is 0, if and only if the rank of tau is the dimension of v. Or in other words, the image of tau has the same dimension as the domain of tau. Okay? So tau is injective if and only if it preserves the dimension. The dimension of the image is the same as the dimension of the domain. No shrinkage of dimension. In particular, and this is the most important case, if v and w have the same finite dimension, it must be finite, if they're equal dimension, then tau is injective if and only if it is surjective. That follows from the Rank-Nullity Theorem. And that's quite amazing. For an ordinary set function, say here f mapping sets x to y, the concepts of injectivity and surjectivity are totally unrelated. There are functions, and I'll let you produce examples, set functions that are injective but not surjective, surjective but not injective, both injective and surjective, and neither injective nor surjective. All the possibilities can occur. But with linear maps between finite dimensional vector spaces of the same dimension, the two concepts are equivalent. Injectivity if and only if surjectivity. And that's a remarkable theorem and a very important one.